Go ahead.
Yeah,
Good luck.
thank you. Actually, I'm speaking more about this IoT thing. So, what is IoT? How many of you are following Internet of Shit on Twitter? It's the name of a Twitter handle. I'm not trying to be difficult here. Yeah, not so many. So those of you who do might have come to the conclusion that IoT means that I take something, a thing that existed before, like a switch for a light in my home, and I connect it via the internet to some service in the cloud. And then I can do stuff with it. So I can talk with that cloud service from my mobile phone, for example, when I'm sitting on the couch, and I can switch on and off the light. Notice how this is just using the internet as a transport between this light switch and a service in the cloud. So I don't think that really is an Internet of Things. What does Internet of Things mean? What should it mean if we just look at the English words? So you take things, multiple things, it's the plural form, and these things form a network. There are multiple things that are working together, that are communicating, that are a network. That is a network of things. Now, what would be an Internet of Things? It means that it's not just one network, it's multiple networks spanning the globe, the internet, that are now having all these things in them that make up this network. An example here, also home-based, is I could have a delivery drone that comes flying to my home. It's owned by some company. I don't care which one, but it's not owned by me. And I have this vault, delivery vault, somewhere in my house where the drone can deposit something. Perhaps that is how it works sometime. In Germany, that's definitely not yet how it works. So the drone comes, and it's a thing. And the vault is sitting there, and it's a thing. They didn't know each other before. They had no contact whatsoever. Drone comes, communicates with this other thing to say, here I am, these are my credentials, please open, I want to make a delivery. And then the vault checks that and says, yeah, okay, you're clear. Opening some hatch or whatever, and lets the delivery take place. This is something that I would find useful. I mean, sitting on a couch and not getting my ass up to just switch the light on and off, yeah, I don't really buy that. But this communication across boundaries, that's where it becomes interesting. This example also shows that the Internet of Things means that the things communicate with one another. Otherwise, they don't really form a network. Otherwise, they do not collaborate. Otherwise, they do not create the same kind of value. So let's take a look at this example again. You have this drone that's flying. It has lots of software on it. Real-time controllers, routing planners, whatever. It also has one piece of the software, one module. You could call it a microservice if you want. I don't really care how you call it. It's this piece of software that's responsible for speaking to the vault, where the delivery is going to take place. On the other side, the vault also has much software, and some part of it, one module, little service, is supposed to be talking to a drone that's coming and making a delivery. Now, the Internet of Things, to me, means that we have these two parties that are both on things, that are autonomous agents that collaborate, that communicate, that make something happen. Autonomous agents. That's how I would like to call them, because you can look those words up in a dictionary and you will probably come to the right conclusion. I like terms like that everyone can just look up. So, we are having these autonomous agents, and now we need to make them talk. And that is what I will speak about in the remainder of the talk. Now, for the context that I'm coming from, I'm CTO and founder of Actix, and we do software for factories. So factories are places like this. Factories are not only like the BMWs with all the robots and so on. They are mostly places where something somewhat dirty happens, value is created. This is, for example, turning sand and potassium and all these other things into glass bottles. So this is a glass-making machine. It needs to be there because otherwise no one can fill medicine in these glass containers. So what a factory does is it takes some input materials. It uses machines, labor, and other resources to turn these input materials into some more valuable output material. You turn essentially the sand and the potassium and so on into glass bottles. So not only glass, but specific shape that is useful. And there is a value created here because now someone can fill in some medicine. What is important to understand is this machine here that you see a small fraction of, it's actually a pretty big machine, it has a lot of cost in acquiring it, in maintaining it, keeping it running. So while this transformation from inputs to outputs is happening, revenue is generated, and it costs money for the machine, for the personnel, for electricity, for all the things. While the machine is not running, it does not generate revenue, but it still costs money. This is very important to understand factories and why factories are seemingly so far behind when it comes to software. Some of them really are far behind. When you compare to what we are doing on our phones, well, factories still look like that, and factories do not use software to the same extent. And we'll see why that is. So, important point, time is money. The machine must be running, or the personnel, the craftsmen, operators, they need to do their work. Otherwise, it just costs money and doesn't generate revenue. Now, another thing you need to know about factories is that a factory is a constrained environment. It is a place where you cannot just do whatever you like. There are rules. And these rules are there for good reasons. So if you don't follow these rules, you might get injured. Or it might lead to big losses. It might be that the factory makes so much loss that it needs to close down and everyone loses their job. So there are rules that are there to make sure that the factory is successful and that the personnel are safe. For example, there are typically lines on the floor, and you need to stay within these lines if you don't wear specific safety shoes. These are not safety shoes, so I couldn't go into a factory like that. Or you need to wear a protective helmet, like this guy over here. People are used to following rules in factories because it's good for them and good for the factory. And they are paid to follow these rules. This is pretty important when it comes to software. Because when we install software in factories, it's a different environment than if we were to, say, create the next social network, which needs to work on everybody's phone, and everybody will use it. That's completely different. That's an unconstrained environment. So, in a factory, people are used to following rules. How do these rules nowadays, in most of the factories, how are they communicated? They are communicated via paper. Paper is extremely resilient, extremely reliable. You have a sheet of paper, you have a pen, you can write on the paper. It doesn't matter whether the Wi-Fi is on or off, whether there's electrical power or not, you can always do that. And even if the Wi-Fi goes off, what you have written stays on the paper. That's so awesome. That's not true for a tablet with many traditional applications, for example. You can also take the paper and completely crush it, put it in your pocket, take it back out, and it still works, right? So, I mean, you can destroy paper, of course, but it is very reliable, and that is why it's used a lot in factories. Paper is also local, extremely local. Everything I do with the paper, I need to have the actual paper. I cannot read a paper from afar. I cannot amend what's on the paper from afar. And these are the reasons why factories are really interested in replacing paper with something else, with something more dynamic, something that they can control, where they can embed workflows and model them, software, in other words. Software would be hugely beneficial, but in this special environment, software has not yet really started to gain that much traction. Another thing is, factories, I mean, this one is this glass business is particularly dirty. That's why I chose it. There's lots of grease, and there's lots of like little glass droplets flying around, and there's all sorts of things that you normally don't want right next to your computer. So if you want to run software in a factory, you need to do so on suitable devices. They are usually also a bit constrained. I mean, if you buy rugged tablets, they are not Android 9, they are Android 6 or so. So all these kind of things. So it's a bit of a special location. Now, let's take a look at what we might want to use software for in a factory. Let's say, so this is now idealized, yeah. So this was the only dirty picture. Now I have the idealized world here. There's some machine here. Let's say it's a machine that produces the housings for valves. It's a steel piece. You need to drill and cut and chip and whatever different pieces so that you can then place the valve inside and have the finished product. So this is done in such a multi-purpose machine that can use different tools on the same workpiece, and it runs a given program. These programs exist since a long time. Inside these machines, there has been software for several decades. That's completely usual. Because it's well encapsulated, it's a yet more constrained environment. So the machine knows how to make these valve housings. Now, here's an operator walking past this machine with a tablet in their hand. What does this mean? So usually you need a person to check whether the machine is doing the right thing, whether it's still working correctly. You need a person to tell the machine what to do next. You need to have a person that registers, okay, this is now for the order number 4711, and next one will be for 4713. Someone needs to do all these things. The machine knows what it is doing. The human normally knows a lot more about the context of why that is happening and how it should be happening. So there's a lot of communication going on here because the machine needs to tell the tablet what its status is, how many pieces have been produced, and so on and so forth. So the tablet needs to know this, and the tablet might have a start button that enables the machine to start. So human has checked everything is in order. Yeah, there's a little black strip appearing sometimes. So human has checked everything is in order with the machine. You have a go, and then the machine gets this information and then starts running this program. That could also be how it's done. So this is a use case where we have a person being made somewhat digital capable by having a tablet, and we have a machine, and they are communicating, they are collaborating. They are working together to get these valve housings done. Now, looking into the future or different use cases, it would be possible to add many more things to this mix. For example, the machine might be communicating in general, shouting, oh, I have done these pieces. Here are 12 new pieces that are ready. I've put them on my output tray. And then a drone might come by and fly, hover over it, and use optical sensors or other things to do a quality inspection. Normally, so nowadays, a human goes there and takes a look and measures some things. This could be done also by a drone. And the machine that produced the valve housings would need to tell the drone what to do and when to do it. Or there might be a robot that then picks up these dozen pieces and puts it on an autonomous transport vehicle there at the bottom that will then bring these into the warehouse and put them in the right location. So these are workflows that happen in a factory. Inside the machine, software was always there. Outside, It's all done by paper now, but that will no longer work once we have all these machines. One thing to note here as well is that when these machines start talking, we know that they can get pretty chatty. So they might want to exchange more data. This robot has cameras, and it might want to send them to something else so that they can coordinate, or two robots collaborating might need to exchange a lot of data. And here it's becoming increasingly clear that sending all these data to the cloud and then back will not cut it. It will have too high latency, and the bandwidth will be too limited. So wouldn't it be nice if this happened just on the shop floor, just from one device to the other, without any indirections? So how would we want to model this? How are we modeling this at Actix? We have all these players on the shop floor. We have a machine, we have a robot, we have two persons in this example, and they are all communicating. How is this communication modeled? It's done by everyone publishing what they know. Because in the end, communication is nothing but the transfer of knowledge. I know this, I want someone else to know it. That is the most basic thing. So she up there on the tablet might say, go and write it to some event log. We really believe in recording what happens in a semantically meaningful way, which means event sourcing, domain-driven design, and all that. So there's a machine may start event that is recorded. Someone has pressed the green button, so that's the go signal. And then this machine will look at the event log and scan for this relevant event. Like, am I allowed to start yet? Am I allowed to start yet? And when the event arrives, the machine will start. So doing it this way means that all communication, so everyone emits their own knowledge that they want to share, and everyone can listen in on that. Of course, there can be ACLs, there can be stream names, there can be access control of many kinds. You can encrypt things and so on. But in principle, this event log is a shared place for all these players on the shop floor, producing data and consuming data. So everyone does that with their own business data. Like I said, you press the green button. This can also be done to monitor the whole factory infrastructure, including our own infrastructure as well. So we can send metrics events to this event log. Like, this tablet has 80% battery power, the disk is 56% full, and we have, 1 gigabyte of memory used by that application. This all can be also written in the event log, and it's hugely valuable because then all we need to do is look at the event log to figure out what state the factory is in. We can, from remote, see what is happening and how that is happening. This is very valuable. It's also valuable to keep this information around, sign it, be sure that we know, okay, this was not altered. We have all the history in a log. We take hashes, for example. I mean, something, blockchain, something. And then, in the end, you can have a single hash that describes the state of this factory at this certain point in time. Because I know this is the event log that I reference, that is hashed by this hash, and everything is fully auditable. We know who has spoken to whom about what at which time. So this is what we can do with an event log. Now, this looks a bit weird because I said availability is everything. So it must not ever fail. Machines must be running because time is money. And now we put this big thing in the middle. What if this big thing fails? It cannot. So this is a bit of a conundrum. So let's spell that out in a bit more detail. When we say event log, we need one that has several qualities. It must always be available for writing. So I'm producing new knowledge, I'm recording that, and I want to depend on that everyone else can learn that, who needs to know it. So I need to always be able to put knowledge into the log. It cannot be impossible. So the tablet is running, it needs to be able to publish to that log. What does that mean? Always. It's a big word, it should be all caps. Always means, well, I mean, if the tablet is not running, it cannot produce things. So if it's running, it must be able to produce. If the Wi-Fi is off, it still must be able to produce. That means it must write locally. Writing locally must be good enough while nothing else works, because otherwise we need to stop. Secondly, since everything is modeled as these events are the source of truth. So locally, if I want to update my state, if I want to progress, I need to do so based on the events that I have emitted. So I need to be able to read from the end log at all times, even when the Wi-Fi is off. So I write something to the log, and I need to be able to read it back for myself, at least. Otherwise, I cannot make progress. Not making progress means machine stops, time is money, we don't want that. So these 2 points are a very, very powerful restriction, because it's impossible to work with consensus-based logs here. So we cannot have a log that requires, like a quorum. We cannot have a log that requires distributed agreement on anything, like whether the event has been emitted or what its ordering was or whatever. We cannot have that, because as soon as we switch that on, when the Wi-Fi goes down, the machine stops. We can't do that. So we cannot require consensus. It's excluded here in this case. That's the first very big choice that we've made. Now, what happens after a partition? Say we have this log, it has been appended on multiple sites, and now we have a partition. So we have, for example, the tablet and the machine, and the Wi-Fi is off for a brief period, like 5 minutes, and then someone fixes it. So on the tablet, things might happen. On the machine, things might happen. Knowledge is generated. Now, when the Wi-Fi comes back on and these machines can talk to each other again, they need to synchronize. They need to exchange all that knowledge and get up to speed with what the others have been doing, exactly like us humans do. So I'm flying to San Francisco on Saturday, and I'm meeting some friends, and we'll be catching up because we've been separated. And yeah, so that's what we do. We just chat. We communicate. We exchange knowledge. The good thing here is, since we are using event sourcing, that means we're only ever appending events to the log. We're only creating new knowledge. We are never modifying old knowledge. We are not removing old knowledge. Synchronization is actually not that difficult. We just need to make sure that everyone has all the events. Yeah? It's a pretty simple merge operation from that point of view. So then, once everybody has all the events, and they run the same queries, the same questions across these event streams, they will all come to the same conclusion, and everyone will be synchronized and up to date. So that's awesome. There's a fourth point I would like to mention, namely the reader, so whoever reads from this log, determines when they do that, how fast they do that, what they want. So this is not push-based, this is really pull-based. So I can add knowledge to the pool, but nobody is really forced to ingest it. How could it work? I mean, if I commit locally to my log, I add new knowledge, Wi-Fi is off, no one can see it anyway. Or another thing is, we don't know who will be reading it. So the factory has been running for 10 years, and then someone wants to run an analysis on what happened over the 10-year period. So that's a new reader that we didn't know about upfront, who then comes much later and chooses to get everything delivered. So this is an important one, because it forces us to have unbounded buffering, if you will. If you were to do this in Kafka, you would have to set the retention time to infinity. Otherwise, the reader would be limited in their choice when they want to consume the data. So we want a log, to summarize, that is always available for reading and writing, which excludes consensus because of the synchronization problem. We want synchronization to happen and it needs to be infinitely durable. Oh, I forgot one point. Synchronization. So communication between these machines is important to make progress. So if I press that green button and the machine doesn't start running, that's bad. So if the Wi-Fi is off, yeah, okay, then I fix the Wi-Fi and then I expect it to work. What I cannot tolerate is that this is working, the Wi-Fi is working, this is working, but it still doesn't synchronize because it goes via the internet, via some cloud service. Synchronization must work as well as it possibly can, as locally as it possibly can. Okay, so we have that. We know, okay, a log is just a heap of knowledge. It's a huge number of events that is always piled upon. So the interesting question now, the one remaining crucial question is, how do we sort that heap? How do we deal with it? So this is an example that illustrates the point. We have new events coming in. These are the orange ones. And so let's say in this example, there was this woman with a tablet walking past the machine, you remember. And so on the tablet, you can press start and stop buttons. You can say which order it was. And the machine says how much was produced. Let's say these two new events are the ones from the machine that say how much was produced. And let's say there was a partition. So everything started, and then there was a partition, and the machine was recording what it produced, and on the tablet you recorded that now the order has ended, but only then the partition heals. So what do we do now? There are two choices. On the left-hand side, we have local discovery order, as I would call it. So this is new knowledge. For example, on the tablet, it comes from the machine, goes to the tablet. And this new knowledge is just appended to the local log. The local log is an append-only log. Now, that's pretty useful. It means that it's very simple to write this code, so I can just add the events at the end of the log, always piling onto it. But when I then want to write code that makes sense of these events, this code now needs to deal with the situation that they arrive out of order. And a lot of points apply that Greg Young made yesterday evening about timing in event-sourced systems. So now we have the stop event for the machine, and then afterwards we get the records of how many pieces were produced. And it's kind of hairy, because then how do you make sure that you correctly attribute these like 12 pieces to the correct order that they belonged to? It is doable, definitely. You can send around timestamps and so on. But writing the code is harder this way. What if there was a way... there's one important point. The logs on the different sites will have different ordering. They will contain the same events, but the machine will have a different view of the order in which things happened than the tablet. Yeah? So your code is responsible for making the whole thing eventually consistent. That's the hard part that I just meant. Now, what if we had a way to know beforehand, without coordination, in which order things belong? And everyone would come to the same conclusion. So if everyone has the same set of events, and they apply their ordering algorithm to the events, everyone will have the exact same copy of the log. That is displayed on the right-hand side. That's what I would call eventually consistent order. Eventually consistent because it may take time for all the events to get everywhere. But once everyone has all the events, they will all have the same log. It will be consistent. So I use these numbers here to make it clear that there is this kind of ordering. How would you get such numbers? Well, you could, for example, use GUIDs for each of the locations. So for the tablet, it has its own ID, the machine has its own ID, and there is a sorting relationship between these two IDs. You can just sort by string sort if you want. And then you need at least one other thing, which is a sequence number, the sequence of events emitted by each device. this would be a total ordering. If you order by this tuple, it would be a total ordering. It would not be very useful, though, because a device with lots of events will typically be applied, have its events applied later than a device with just a few events. So it is very useful to include a timestamp in there. There are different choices of timestamps. You could use the device clock. It has its charm, but it also has its problems. Namely, if there is clock skew, then you get causality violations. If you don't want causality violations, then you just read literature from the, I think, 70s, Leslie Lamport, Lamport clocks and Lamport timestamps, and that gets rid of the causality violations, but it has slightly different problems. Or you go full causality tracking, which would give you the best ordering that you can possibly have in this scenario, but it is expensive. You need to track lots of states. So yeah, you need to make some choices here, what you want to use. But the point is, you can make it such that you can get this deterministic ordering at all sites. What does that mean? I now can write code that looks at these on the right-hand side. It looks at these events and applies them. And as long as the code is deterministic, it will always come to the same conclusion on all the sites. I can run it in different places. It's automatically eventually consistent. It also means that the code has run on these 5 events previously, and now these 2 new events come in, not at the end, but somewhere in the middle, and then I need to run the code from the state that it was in at event 1085, and then continue upwards. So I need to do some time traveling here, but we should all be used to that by now, because that's what Bitcoin does. Bitcoin chooses the longest chain, and then it only takes the transactions that were on the longest chain, and that's the authoritative thing. So if you want to know what's in your wallet, you need to evaluate the longest chain. So same thing here. There's quite a lot of research. It also appeared at this conference about how you can deal with the local discovery order on the left-hand side. There are data types that started appearing in the 80s and that have seen a renaissance in the late 2000s, which are the CRDTs. Those are conflict-free replicated data types. And they have the property that the order doesn't really matter, or the order can be figured out, and so the algorithms vary a bit on how it works. But these data types, if you compute these specific data types from this thing on the left-hand side, you can also achieve eventual consistency. It is guaranteed by the data type that no matter which order I get the stuff, I will come to the same result. These data types have some restrictions, though. They are not completely free in what you can do. There are many useful ones. There are maps and sets, and I mean, Helena showed some yesterday. So there are many useful things, but still, there's a JSON one, for example, that tells you kind of what is possible. But not everything is a JSON thing. So you can, on the left-hand side, use that, or on the right-hand side, you can write code that does whatever you want. Now, there is one other thing that distinguishes these two, which I would like to illustrate here. Let's say we have this one log, one application, one shared data type that we are coordinating. And let's say we are using these conflict-free replicated data types. We'll be sending around, so we'll be creating knowledge on the left-hand side in this universe in the form of so-called deltas or operations. They describe how the data type would change. So if I manage a list of orders, I could insert one at position 5. That would be an operation, and that would be the fact that is noted down here as an operation or as a delta. So within this universe, this all makes perfect sense, at least to the machine and to the, for example, to the delta CRDT algorithm. Universe B over there is some other context. It is not in the app. Universe B might be the developer's brain. like we need to know, so we need to transfer, okay, I see this in the log, this specific delta here. What does it actually mean? So I need to make the transfer into my understanding domain, and that is pretty much unclear for these. It's really technical what these deltas look like or what these operations look like. The whole context for understanding them is embedded in the universe on the left-hand side. So you would need to transport all that and analyze it together and then come to a conclusion what this delta actually represents. This is why we are not using CRDTs. We are using events. We are using semantically meaningful events to describe things that happen on the shop floor in our case, so in this universe A. And then there is a translation to a universe B. It could be a translation to the human brain by reading a documentation of this is our domain model and this is what this event means. It could be also another application. So you have this machine control application or production data acquisition application here. You might have a completely different application that's focused on intralogistics in a factory. That will be universe B. And you're interested in when a machine has done something, so you can transform that event into from the machine has done something into new finished goods have appeared at this location. These are corresponding events. You can translate them between them with your domain knowledge that you have inside a factory in this case. And so you just need to know the name of the event on the left-hand side, and then you can make the event on the right-hand side. And people can understand it. So this is why we are using events that are meaningful. We are using event sourcing. Now, this is a little detour. Not everything, so I mean, we've built lots of stuff, that's what we do. Programmers like to code, programmers also throw away lots of code. But standing on the shoulders of giants is always helpful because you get a much better view. So this is IPFS, the Interplanetary File System. It is, I mean, the name is not a joke at all, right? It is meant to work even between Earth and Mars, for example. So clearly, this is the right tool you want to use if coordination is not really an option, because light speed is too slow to make that work, really. I mean, you could have coordination for very, very important things where you can actually wait the time, but normally not. So IPFS is built on this premise that there is no coordination whatsoever. You can find data by its hash. It's a content-addressed storage. So you can put data into IPFS, that's the file system part, and you get back the hash. And then when you know the hash, you can ask for the data. So basically, you have the fingerprint, you can ask for the person, or kind of like that. If you don't have the hash, you cannot get the data. Now, IPFS makes sure that all the nodes that participate exchange regularly which hashes they know about, so when you ask for a hash, you can actually get the contents behind it. That's one feature we use. Another feature is that you can publish on a topic and subscribe elsewhere. Typical PubSub, but it's in a completely peer-to-peer fashion. There is no central servers. I just say something, and then the network figures out where it needs to go to reach everyone. To reach everyone who needs to know it. So those are the features of IPFS that we are using, and we are storing our events in IPFS as these blobs. That's where you could say that we are doing something like blockchain. And we're using PubSub for communication, and the devices discover each other, and there's much of code we didn't have to write. Okay, but that was just an aside. So coming to the summary, distributed systems, everybody knows, is only about communication. Communication gets a lot easier when it's restricted to immutable facts. When you say something and you cannot retract it, you cannot change it after the fact, because then you can just ship around the facts and you don't need to worry about coordination. So communicate immutable facts. And then based on the local understanding, on the local knowledge of each node, you make decisions. Now you can choose to not decide while you're waiting for more information to form consensus and so on. So if you have a system that is without coordination, you can build one with coordination on top of it. But this is the minimal basis. And this is what we chose to make software that can actually replace paper in its reliability. Yeah, I have a tablet, write on it. As long as there's electrical power, that's the difference, it stays there. The knowledge doesn't vanish. Just like on the paper, I wrote on it, stays there when the Wi-Fi is off. Thank you.
So, thanks very much, Roland. I think we're a little bit over time, so unfortunately we don't have time for questions, as we need to prepare for the next speaker.
Yep.
It was very interesting. So if you have more questions for Roland, and I think he has much more to tell us, please find him in the coffee break. And I would like to thank him, give him a warm applause, and hope to see him next year.
Thank you.